Imagine you're in a hospital delivery room and the air around you is quite tense. A mother is about to give birth and the doctor wants to know where is the baby's head. The answer can mean a safe natural birth or a complicated procedure. Doctors use an ultrasound scan, a device that sends harmless sound waves, to take a real time look inside the mother's womb. But the baby can be in many positions. Accurately finding the baby's head and the mother's pelvic bone helps make the safest decision. Hello, my name is Amna Ijaz, and in this video we will uncover the journey from ultrasound to intelligence. Assuming that the doctors have an ultrasound, but interpreting these images is hard even for experts. But what if computers could help? For that, we need high quality labeled ultrasound data, and that's where my project comes in. Our dataset contains 1,000 carefully annotated ultrasound images, each showing the exact position of the baby's head and the mother's pelvic bone. These labeled images are essential for teaching artificial intelligence, helping computers see what doctors see. We trained a neural network to spot these features automatically. To make it robust, we use data augmentation, which slightly changes the images. This helps the AI handle the real-world variations. Let's begin our journey by setting up the foundational building blocks for our deep learning pipeline. Here I am importing all essential Python libraries and modules. I am also including libraries for data processing and augmentation. To ensure our experiments are reproducible, I set a random seed across all relevant libraries. First, we gather all the ultrasound images and their corresponding masks from the dataset folders. Next, our custom dataset class loads and processes each image mask pair, making them ready for training. We also normalize the images and prepare them for augmentation. Finally, we count the frequency of each class in the dataset to handle class imbalance during model training. In this section, we apply data augmentation techniques to increase the robustness of our model. We use elastic deformation to mimic anatomical variability, intensity shifts to simulate different scan conditions, and Gaussian blur to account for imaging artifacts. For our model architecture, we use a UNet, which is popular for biomedical image segmentation. It features an encoder-decoder structure, capturing context with downsampling and precise localization with upsampling. Double convolution blocks extract rich features at each stage. This design helps our model accurately segment anatomical structures in ultrasound images. In this step, we define how our model learns and how we evaluate its performance. We use Dice and cross entropy losses to optimize for accurate segmentation of each class. Metrics like Dice score and IOU help us improve how well our model predicts the target regions. Together, these ensure our model isn't just learning but actually improving with every epoch. In this step, we train our UNet model using 5-fold cross-validation, ensuring robust and unbiased results. For each fold, we split our dataset into training and validation sets, and then train the model for a set number of epochs. We use an optimizer and a combined loss function shown previously to guide learning and evaluate performance after every epoch. This loop allows us to systematically test the model's ability to generalize across different parts of the dataset. First, we train our segmentation model without any data augmentation. These scores set our baseline performance, reflecting how well the model learns from the original unmodified images. Next, we introduce data augmentation during training. As a result, we see even higher average Dice and IOU scores, demonstrating that augmentation not only boosts model accuracy but also improves its robustness to real-world variations. Here we see that models trained with data augmentation consistently outperform those without, achieving high Dice and IOU scores across all folds. To explore the code, you can visit my GitHub repository. And for accessing the full dataset and documentation, head over to the Zenodo link. Both links are provided for open science and reproducibility. Feel free to try it out and contribute.